All right, so hydroboration followed by oxidation. This is a fun one right here. So let's say we have an alkene and we have BH3. That's a boron, right? Um, and then when we add the BH3, um, we add the BH2 on one carbon and the hydrogen on the other carbon. That makes an alkyl borane. Okay. And now the second step of this particular reaction is called as the oxidation step. That's H2O2 as well as hydroxide. So hydrogen peroxide and hydroxide gets you that alcohol product, and the OH just replaces the BH2. So that's the oxidation step, and then the one before that is the hydroboration step. Okay, that's where it gets the name hydroboration-oxidation. So that OH group, it just replaces the uh, the boron compound, like the BH2, and it maintains the configuration that it has. Okay, so the chemistry occurs at that boron site, and it's kind of a fancy mechanism that's kind of we don't need to worry about, but we do need to understand that the mechanism yields the same configuration. Okay, so for example, if we had a BH2 with a wedge, and then we do the oxidation step, then we would get the alcohol with a wedge. Okay, so I understand this compound is not ideal for the example, but I really just want you to focus on the wedge. Okay, so same configuration because the chemistry is occurring at that uh, site right there. There's nothing else going on. And so when we add the BH3 to the alkene, we have to focus on the difference in electronegativity of the BH. So the hydrogen is actually more electronegative, and the boron is therefore delta positive, while the hydrogen is negative. And so this is when you're talking about BH3, you're always talking about hydrogen as a hydride. So we've seen sodium hydride, it's a negatively charged hydrogen, and that's really what BH3 is a source of. It's as if we're adding an H minus to this compound, okay, to the alkene, okay. So we've got a trigonoplanar electron deficient boron trihydride, and if a Lewis base comes along, it can kind of occupy that vacant p orbital. We already know this stuff. So, and that makes a Lewis base adduct. Okay, and typically when you buy this BH3, it's not just going to be BH3 in a bottle. It's actually going to be a Lewis acid base adduct, and it's sold with like BH3 with THF. Okay, so that's what this heterocyclic ring is, and you get the negative and positive charge on the boron and oxygen respectively, and then that's THF on the upper left. Okay, so just so you know, it is a very reactive compound, and that's why it's sold as an adduct. Okay. The mechanism is the alkene attacks the boron because it's positively charged, right? And then in a concerted fashion, the hydride actually attacks what would be the carbocation, right? But by concerted, we mean it all happens at the same time. And so we get syn addition of the BH2 and the hydrogen, okay? And again, that's called because we have a concerted addition of the BH2 and the hydrogen, okay? And this is not necessarily important for maybe this cyclohexene, but once we start adding in unsymmetrical alkenes, then we definitely need to know this, okay? All right, I told you classifying as regioselective, not my favorite, right? It's kind of like whatever, who cares? Like Tom Hanks and Jordan Peele, like, okay. So why am I writing this? Okay, well, it's just kind of the nature of this reaction. If we have this methyl cyclohexene and we have our BH bond that's going to add to that alkene in a concerted fashion, which orientation do you think it should approach? Or does it matter? Okay. Well, I'm labeling the borons as blue and the hydrogens as red because blue is electrophilic and red is nucleophilic. Okay. We also have this pi bond red. That pi bond wants to attack an electrophile, and it's going to do this orientation. And why is that important? Because once it attacks, it's almost like there's a carbocation intermediate. Okay. And that hydride can now attack that carbocation intermediate. And again, I'm only saying this as if it were a two-step process, but it is a concerted addition of that BH, okay? And again, as a syn addition, okay? And so we get this alkyl borane right here after hydrogen peroxide and hydroxide addition. We get the oxidation to the alcohol, okay? And that's pretty much that's the idea of regioselective. You're always going to get the alcohol at the less substituted carbon. Okay, we'll come back to that though. So let's draw the different isomers. Okay, well, I'm going to draw a bunch of wedges and dashes here for you, but let's run it through with my super duper amazing drawings. So that way you can understand really where the products are coming from, and rather than me just telling you, right? So again, I'm trying to draw this. I should just leave the sentence there. Yeah, we're trying to draw this, but for a different point of view. Okay, so we're almost like flattening that ring out, and we have the BH approaching from the top. Okay, and once that attacks, that forces the methyl down. And what we get is the boron and the hydrogen in the up position with the methyl down. Okay. And what that means is after the oxidation process with hydrogen peroxide and sodium and hydroxide, we get the alcohol on the top and the hydrogen on the top and then the methyl on the bottom. Okay. So remember, when you're drawing it like this, you have the alcohol up and the hydrogen up. That means those would have the wedges in the when you're drawing wedges and dashes in the upper rings. Okay, so we can write that in now. The one on the left is got the OH as a wedge. Okay, now how do we get another product? Well, it's all about the approach of that BH3 again, and it can approach from the bottom. Again, that concerted addition of the BH across that alkene results in the boron and the hydrogen projected downward while the methyl is projected upward. Okay. After oxidation with hydrogen peroxide and hydroxide, we get the formation of the alcohol in the down position, and then that translates to the alcohol in the dashed position in the upper structures. Okay, so that's how we end up with our two isomers. Okay, what's the relationship with these? If you flip the one on the right, then you'll see that they're non-superimposable mirror images, aka enantiomers. All right, so what's up with this OH being on the less substituted carbon? Okay, so this product, if we were just going to look at it as it is, we're going to think like, okay, well, we went from an alkene to an alcohol, and the alcohol went to the least substituted position. That's not Markovnikov's rule, and it's actually called anti-Markovnikov addition of that OH there. Okay, and in actuality, it really is Markovnikov, because in this case, hydrogen is the nucleophile as a hydride, and it does add to the more substituted carbon, right? But if you just look at the alkene and then look at the product, it does give that perception that it was an anti-Markovnikov addition of that OH to the less substituted carbon. And so that's one thing that's really useful about this process, is that you do get the OH at the less substituted carbon. And there's no rearrangements. Of course, those are always nice to avoid. because there's no carbocation intermediate, because there's a syn addition in a concerted fashion of that for that BH being adding across that double bond. Okay. Now here is that chart from the other videos. Well, now we get to complete our chart. Yeah. Okay, so let's remind ourselves the addition of. Oh man, I forgot about these methyls here. That's messed up. Y'all didn't even tell me. That's messed up. Okay, sorry. Let's remind ourselves where these OHs go and where the methyls go. When you have the BH3 and the hydrogen peroxide and hydroxide, you're doing anti-Markovnikov addition of that OH. And so you also want to remember that your OH and your hydrogen are going to have, since they are syn, they're also viewed as cis when you're drawing like the wedges and dashes. A couple notes here, anti-Markovnikov obviously, and then syn addition. Okay. Now, this is pretty much a full chart now, right? That's awesome. We know things. We're going to use this for synthetic chemistry. It's going to be super useful. But these two right here, these are the things that point out the synthetic utility of the two different reactions. We get the two alcohols, or actually four alcohols, but at two different carbons. Okay, so let's talk about practice. Let's just do a couple. This is actually more like synthetic chemistry, so we're applying the possibility of multiple reactions that we now know, being in chapter, I don't know, like 52 it feels like. So we really want to figure out how to make the compound on the upper right from the one on the left, and then the one on the right, bottom right, from the one on the left. Okay. Now, what we really want to do, the way we approach this, is just kind of understand what we have and what we know. So, what is, that was a terrible question mark. What is this? Okay, it's a halohydrin, right? Or a chlorohydrin. And we know how to make this, right? We just learned. So, how do we do this? Well, the retrosynthetic arrow going backwards, we know we can make this from an alkene. Okay, so what reagents with that alkene are required? Well, it's chlorine and water, right? Okay, well, if we know how to make that chlorohydrin, how do we make the alkene that's needed to make that? Okay, well, how can we go from that bromobutane, we add chickenfoot, right? Or DBU or DBN. Basically, just a strong base, ideally non-nucleophilic, just so you don't get byproducts, but a strong base will give you that alkene product. And then you add the chlorine and water to get your halohydrin. And that's it. That's all she wrote. Super fun. This is a straightforward mechanism or problem, I guess. They can get more complicated. But this one right here, we have two alcohols, a tertiary and a secondary, right? Now, how the heck do we do this? How are we just swapping stuff out, right? Well, you might be inclined to think about this alcohol being at the secondary position, like one of the products we made above. And we can make that from this alkene, methyl cyclohexene, with the BH3 and hydrogen peroxide and hydroxide, right? In a two-step process. And we know that's the anti-Markovnikov addition of that OH. And how do we make the alkene from that tertiary alcohol, though? Anybody remember? Yeah, strong acid. Okay, we can do sulfuric acid or paratoluene sulfonic acid. It's just a strong acid with a weak conjugate base, and then you've got your desired product. So let me know if you have any questions. This is the fun part. We're starting to do synthetic chemistry, so multi-step stuff too, though. So get that practice in, because you really need to kind of make sure you have all your reactions down, so that way you can do these multiple step processes. Okay, bye.